All right, so let's pick back up where we left off and start going through the rest of the derivation here. If I can find my notes. Okay. All right, so we're now on to step 4, where we need to take our ODE, this is our ordinary differential equation in heat in terms of Q, and we need to now come up with an expression for Q dot, right? We need to take our rate equation that governs Q dot and sub it into this equation. So that is Fourier's law. So we're going to say, let's see here. So we use Fourier's law, which is Q dot double prime R equals minus K partial T with respect to R. We want to express this in terms of Q dot, not Q dot double prime. So we need to multiply by the area. Okay, so that's going to be Q dot R is equal to minus K. So what's the area that we are considering here? Let me just flip back to this diagram. So which area are we talking about? We're talking about a conduction area in the R direction. It's going to be the length. It's going to be not dr, right? Because we aren't conducting vertically, right? We're conducting in the R direction. So the area that's available for conduction is actually the length times the circumference of the cylinder, right? So that's going to be minus K times 2 pi R. So R is whatever radius we're at when we're evaluating this. R times L, that's our area. And then we have dt dr. Because this is only a function of R, we can make this, instead of a partial differential, just an ordinary differential, dt dr. All right, so we now have our rate equation. So let's sub that back into our ODE and Q. So that becomes d dr of this rate equation minus 2 pi r times k times L times dt dr. And all that is equal to 0, right? We're just subbing that into this guy here. All right, we're equal to 0, so we can cancel out constants that are contained on the left-hand side. So let's see, we have 2, minus 2 can go away, pi can go away, k and L can go away. All right, and so we're left with d dr of r dt dr equals 0. All right, hopefully that all makes sense and is basically review. One maybe not obvious thing is R is not a constant, so it has to stay inside that inside the argument of that derivative. And we can't do something like take R out and multiply, right? We're taking the derivative of the product of R times dt dr, so it all has to stay inside. All right, so we can solve this problem pretty easily, right? This is a separable problem. We can just use integration to solve this. But I'll just walk through it this one time to refresh ourselves on what we do. So we'll take the dr that's on this side and move it over to the other side. So that becomes d of r dt dr is equal to 0 dr, and we're going to integrate both sides. Right? The indefinite integral of a differential is just the argument, right? It's just the integrand that comes back. So we have on the left-hand side r dt dr, and on the right-hand side the integral of 0 is a constant. So we have a constant. We know we have to do this again, so I'm going to make this C1. Okay, so carrying on, we need to now separate the variables. On the left-hand side we have r over dr and dt. We want maybe the stuff with r to go to the right-hand side. So let's multiply both sides of the equation by dr and divide both by r. And we end up with dt is equal to c1 over r times dr. Right? And integrate both sides. Integral of dt is just t. And the right-hand side becomes, well, the integral of 1 over r is ln of r. So that's going to be c1 ln of r. And then we have to have our constant of integration, right, c2. Okay, so this is the general solution, this here. This is our general solution for t as a function of r. And what do I mean by general? Just remember, this solution is not specific to our problem yet. We haven't made this solution match our actual boundary conditions yet. This is only a general solution that applies to any conduction in a cylindrical geometry, right? So we need to next go through, take this general solution, apply our boundary conditions, and then make this fit our actual problem. Okay. So I guess it would first help to state what our boundary condition is. All right, so we have two constants. That means we need two boundary conditions to pin those down. So what is, anybody want to volunteer what the first boundary condition might be? Dorian.
T at r equals 0 is th.
Right, so t at r equals 0 is equal to th. Right? R equals Rn. Yep, thank you.
Yeah, right.
R equals Rn. Right, and the second boundary condition for this problem? Very similar. T at R equals R out equals TC, right? Simple boundary conditions. So the way that I'd like you to think about stating these or think about enforcing boundary conditions is first and always write out a statement that says exactly what it is you're trying to set equal at the boundary. So there's different types of boundary conditions, right? We have a temperature boundary condition, which is here we're just saying the temperature equation needs to be equal to the specified temperature. Right? There's conductive boundary conditions or a rate matching boundary condition where you say I know the Q dot at the boundary. So in that case, we need to force the heat equation to match at the boundary. And then there's things like rate-specific equations, like you know the temperature of the surroundings plus some convective coefficient or radiation resistance, and you're going to then calculate a rate that applies at that boundary given those conditions. All right. So those three different types of boundary conditions are things we'll get into, but here we just have the simple temperature boundary conditions. So the way you want to do this is state them in a simple way like this. So you say what the boundary condition is, where you're evaluating the boundary condition, and then we'll go back and we'll actually substitute in the temperature equation or heat equation or whatever that corresponds to this statement. All right, so we can do that. Let's remember here that this is our general solution. All right, T C1 ln of R plus C2. So all we need to do is, let's say for boundary condition 1, we need to evaluate the boundary condition at the correct R and set it equal to the correct temperature. So so boundary condition 1 becomes C1 ln of Rn plus C2 is equal to TH. All right, second boundary condition is C1 ln of R out plus C2 is equal to TC. All right. So look at this. Now we have two equations and two unknowns, C1 and C2. So we could actually go and solve for this. It's pretty straightforward. Hopefully you can all do that algebra. Right? We don't need to go through it here, but you would just solve the system of equations, solve for, say, C2 first, sub that into the second, and you can get the expressions for C1 and C2, and then that becomes your specific solution for this problem. Right? You've imposed the boundary conditions that make it match this problem. Okay. So rather than going through the algebra, what I wanted to show you was let's take this opportunity to look at Maple and learn a little bit about how to use that. Okay.